Over the past 60 years, cosmology has become ever more precise in its ability to account for the best available data about the universe. Many discoveries throughout our history have enabled us to better understand the universe around us. Even though we don't know everything, there are enormous sources of knowledge that have empowered us to draw far-reaching conclusions about our universe. We know what it's made up of in terms of matter, energy, radiation, and so on. We know that there are 400 billion stars within our galaxy and about 2 trillion galaxies throughout the visible universe. We know how the universe clumps and clusters together into galaxy groups, clusters, and filaments, and how they're separated by vast cosmic voids. We know the scale of the cosmic distances defining these structures and how the universe is evolving over time. It's a remarkable story that all fits together beautifully in the framework of the Big Bang and general relativity theory. But along the way, experts have had to postulate the existence of components of the universe for which we have no direct evidence. Up to now, all the stars, planets, and galaxies that can be seen today make up just 5% of the universe. The other 95% is made of stuff astronomers can't see, can't detect, or even comprehend. Worse, when we extrapolate back to the earliest stages of the universe and compare what we expect to observe, there are some big problems. Not long after the James Webb Space Telescope, JWST, began beaming back stunning images of planets and nebulae last year, astronomers, though dazzled, had to admit that something was amiss. 8 months later, based in part on what the telescope has revealed, it's beginning to look as if we may need to rethink key features of the origin and development of the universe. Join us today as we dig deep into how the James Webb Space Telescope has debunked all modern theories of the universe. The James Webb Space Telescope is a breathtakingly glorious feat of engineering. Built on the Hubble Space Telescope's discoveries, James Webb is a giant leap forward in our quest to understand the universe and our origins. It is a premier observatory with a large infrared telescope that has an approximately 6.5-meter primary mirror. The most cutting-edge engineering allowed Webb to examine every phase of cosmic history, from the first luminous glows after the Big Bang to the formation of galaxies, stars, and planets, to the evolution of our own solar system. Launched at the end of 2021 as a joint project of NASA, the European Space Agency, and the Canadian Space Agency, the Webb, a tool with unmatched powers of observation, is on an exciting mission to look back in time at the first stars and galaxies, delivering and giving us a broader understanding of the origins of our universe. But the fact is that the more curious we get about the great cosmic unknowns, the more unanswered questions our investigations of the universe will reveal. Indeed, one of Webb's first major findings was exciting in an uncomfortable sense. It discovered the existence of fully formed galaxies far earlier than should have been possible according to the so-called Standard Model of cosmology. According to the Standard Model, which is the basis for essentially all research in the field, there is a fixed and precise sequence of events that followed the Big Bang. First, the force of gravity pulled together denser regions in the cooling cosmic gas, which grew to become stars and black holes. Then, the force of gravity pulled together the stars into galaxies. The Webb data, though, revealed that some very large galaxies formed really fast, in too short a time, at least according to the Standard Model. This was no minor discrepancy. The finding is akin to parents and their children appearing in a story when the grandparents are still children themselves. Unfortunately, it was not an isolated incident. There have been other recent occasions in which the evidence behind science's basic understanding of the universe has been found to be alarmingly inconsistent. Take the matter of how fast the universe is expanding. This is a fundamental fact in cosmological science, the so-called Hubble constant. Yet scientists have not been able to settle on a number. There are two main ways to calculate it. One involves measurements of the early universe, such as the sort that the Webb is providing, and the other involves measurements of nearby stars in the modern universe. Despite decades of effort, these two methods continue to yield different answers. At first, scientists expected this discrepancy to resolve as the data got better, But the problem has stubbornly persisted even as the data have gotten far more precise. And now, new data from the Webb have exacerbated the problem. This trend suggests a flaw in the model, not in the data. Two serious issues with the standard model of cosmology would be concerning enough, but the model has already been patched up numerous times over the past half-century to better conform with the best available data, alterations that may well be necessary and correct, but which, in light of the problems we are now confronting, could strike a skeptic as a bit too convenient. Physicists and astronomers are starting to get the sense that something may be really wrong. It's not just that some of us believe we might have to rethink the standard model of cosmology. We might also have to change the way we think about some of the most basic features of our universe. A conceptual revolution, if you will, that would have implications far beyond the world of science. A potent mix of hard-won data and rarefied abstract mathematical physics, the standard model of cosmology is rightfully understood as a triumph of human ingenuity. It has its origins in Edwin Hubble's discovery in the 1920s that the universe was expanding, the first piece of evidence for the Big Bang. Then, in 1964, radio astronomers discovered the so-called cosmic microwave background, the fossil radiation reaching us from shortly after the universe began expanding. That finding told us that the early universe was a hot, dense soup of subatomic particles that has been continually cooling and becoming less dense ever since. Over the past 60 years, cosmology has become ever more precise in its ability to account for the best available data about the universe. But along the way, to gain such a high degree of precision, astrophysicists have had to postulate the existence of components of the universe for which we have no direct evidence. The standard model today holds that normal matter, the stuff that makes up people and planets and everything else we can see, constitutes only about 4% of the universe. The rest is invisible stuff called dark matter and dark energy, roughly 28 and 68%, respectively. Cosmic inflation is an example of yet another exotic adjustment made to the standard model. Devised in 1981 to resolve paradoxes arising from an older version of the Big Bang, the theory holds that the early universe expanded exponentially fast for a fraction of a second after the Big Bang. This theory solves certain problems but creates others. Notably, according to most versions of the theory, rather than there being one universe, ours is just one universe in a multiverse, an infinite number of universes, the others of which may be forever unobservable to us, not just in practice but also in principle. There's nothing inherently fishy about these features of the standard model. Scientists often discover good indirect evidence for things that we cannot see, such as hyperdense singularities inside a black hole. But in the wake of Webb's confounding data about galaxy formation and the worsening problem with the Hubble constant, you can't be blamed for starting to wonder if the model is out of joint. A familiar narrative about how science works is often trotted out at this point to assuage anxieties. It goes like this: researchers think that they have a successful theory, but new data show it is flawed. Courageously rolling up their sleeves, the scientists go back to the blackboards and come up with new ideas that allow them to improve their theory by better matching the evidence. It's a story of both humility and triumph, and scientists love to tell it. And it may be what happens in this case too. Perhaps the solution to the problems the Webb is forcing us to confront will require only that cosmologists come up with a new dark something or other that will allow our picture of the universe to continue to match the best cosmological data. However, there is another possibility. We may be at the point where we need a radical departure from the standard model. One that may even require us to change how we think of the elemental components of the universe, possibly even the nature of space and time itself. Cosmology is not like other sciences. It's not like studying mice in a maze or watching chemicals boil in a beaker in a lab. The universe is everything there is. There's only one, and we can't look at it from the outside. You can't put it in a box on a table and run controlled experiments on it because it is all-encompassing. Cosmology forces scientists to tackle questions about the very environment in which science operates. The nature of time, the nature of space, the nature of law-like regularity, the role of the observers doing the observations. Rarefied issues don't come up in most regular science, though one encounters similarly shadowy issues in the science of consciousness and in quantum physics. But working so close to the boundary between science and philosophy, cosmologists are continually haunted by the ghosts of basic assumptions hiding unseen in the tools we use, such as the assumption that scientific laws don't change over time. But that's precisely the sort of assumption we might have to start questioning in order to figure out what's wrong with the Standard Model. One possibility raised by the physicist Lee Smolin and the philosopher Roberto Mangabeira Unger is that the laws of physics can evolve and change over time. Different laws might even compete for effectiveness. An even more radical possibility, discussed by the physicist John Wheeler, is that every act of observation influences the future and even the past history of the universe. On this account, we can't understand what the universe was doing in the past without a more complete understanding of the present, perhaps even the future. These are ideas that scientists have thought about on and off over the past century. We may have reached a point where some of them will need to be revived in a more precise and scientifically credible form. If cosmology does come to require a conceptual revolution of this sort, then the solution to the problem we're currently facing will not come from yet another patch of the Standard Model. Instead, it will require a radically new way of thinking about the universe, one that the James Webb Space Telescope's discoveries are telling us we need. As scientists work out the implications of what Webb is revealing, there may be a better solution to the current crisis, and cosmology will carry on without missing a beat. But the more revolutionary possibilities are now impossible to dismiss, and no one should be surprised if they come to pass.